In this session, let us explore about graphs. Let us see a brief introduction to it. A graph G is equal to V comma E. It consists of a set of vertices V and set of edges E. Here vertices are referred to as nodes. Each edge is a pair V comma W where both are vertices. Edges are sometimes referred to as arcs. This is an example for a graph. Here V1, V2, V3 and V4 are the vertices and various edges includes V1, V2, then V1, V3, V1, V4, V2, V3, V2, V4, V3, V4. So we have a lot of edges here. Directed graph is a graph which consists of directed edges. It is also referred as digraph. In a directed graph, V1, V2 is not equal to V2, V1 because there are some directions specified. So in this case, this V1, V2 is not equal to V2, V1. In an undirected graph, it consists of undirected edges. As you could see, there are no directions or arrows specified in the edges. If this is the case, now we can say V1, V2 is equal to V2, V1 because there are no directions specified here. A weighted graph is one if every edge in the graph is assigned a weight or a value. Here you could see there is some weight or value which are specified in the edges. It can either be a directed graph or it can be an undirected graph as well. A complete graph is one in which each vertex will have an edge to all the other vertices. That's a complete graph. A complete graph with n vertices will have these many number of edges, n into n minus 1 divided by. In this graph, there are 4 vertices. So the number of edges will be 4 into 4 minus 1 divided by 2, which is equal to 6. So there are 6 edges here in a complete graph. A connected graph can be strongly connected or weakly connected. If there is a path from every vertex to every other vertex in a directed graph, then it is a strongly connected graph. Otherwise, it's a weakly connected graph. In this example, in this graph, V1, V2, V3, each vertex are having paths to all the other vertices. For example, from V1, you can move to V2 and you can also move to V3. From V2, you can move to V1 and V3. From V3, you can move to both V1 and V2. So it's a strongly connected graph, whereas here, this is a weakly connected graph. The reason is, from V1, you can only move to V2, but you cannot move to V3. There is no direction here. So this is a weakly connected graph. A path in a graph is a sequence of vertices, W1, W2, W3 till Wn. For example, in this graph, the path from V1 to V3 would be V1, V2, V2, V3. The length of the path is the number of edges on the path, which is equal to n minus 1, where n represents the number of edges. In this example, the length of the path V1 to V3 is 2. V1 to V2, V2 to V3, so 2. Loop. If any graph is containing an edge from a vertex to itself, then the path is referred to as a loop. A cycle in a graph is a path in which the first and the last vertices are the same. A graph which has cycles is referred to as a cyclic graph. 1 to 2, 2 to 3, then again it comes back to 1. It's a cycle. Degree is the number of edges which are incident on a vertex. The in degree of the vertex is the number of edges entering into the vertex. For example, in degree of V1 would be 2 because there are 2 edges which are entering through this particular vertex. When we are considering V4, the in degree of V4 is only 1 because there is only one edge which is entering into the vertex. Out degree will be the number of edges which are exiting from that vertex. Out degree of V1 is 1. It is because there is only one edge which is exiting from V1. Whereas out degree of V4 is 2. There are 2 edges which are exiting out of V4. Acyclic graph. A directed graph which has no cycles is referred to as acyclic graph. It is abbreviated as directed acyclic graph. In the example given here, it's a directed graph, but we don't have any cycles formed. Representation of graph. Graph can be represented by adjacency matrix, adjacency list. Adjacency matrix for a graph G with n vertices is n by n matrix. And A of ij will be 1 if there is an edge from Vi to Vj. It will be 0 if there is no edge. For this graph, this is the adjacency matrix. We have 4 vertices, V1, V2, V3, V4. Now let us consider V2. From V2, there is only one path to V4. So, there is a path from V2 to V4. So, only that particular node will be 1, whereas all the other cells will have 0. Considering V3, V3 is having path only to V2. We can reach only V2. So, as far as V3 is concerned, there is a cell value having 1. which represents that we can reach from B3 to B2, whereas all the other nodes will be 0. Adjacency list representation. In this representation, we'll store the graph as a linked structure, wherein we will store all the vertices in a list, and for each vertex, we will have a linked list of. Now for this graph, this is the adjacency list representation. Initially, all the nodes will be represented as a list, and for each node, there will be a list to all its adjacent vertices. Now consider node 4. From 4, we can reach to adjacent 4 nodes, namely 3, 5, 6, and 7. So this node 4 will have a list to these 4 adjacent nodes, 3, 5, 6, and 7. Now considering node 6, we can't reach any other nodes from 6. There is no path. So as far as 6 is concerned, it has a null value. Graph traversal. It is a way in which you can visit all the nodes in some specific order. There are two types of graph traversal. One is breadth first traversal. The next one is depth first traversal. Breadth first traversal, you start from an unvisited vertex, U. Now from U, we have to visit all the unvisited vertices. Then all the unvisited vertices adjacent to this VI we have to visit, and it goes on. When will the traversal terminate? When there are no more nodes to visit, it will terminate. These are the steps to implement BFS. First step, you will have to choose a node in the graph. That will be the search node. Now that will be marked as visited. Now using the adjacency matrix, you have to find all the unvisited adjacent nodes to this search node. Now all these nodes, you have to enqueue them in the queue. Now each node will be dequeued from the queue. That will be the search node now, which will be marked as visitor. Then these two steps are repeated using the new search node. This process is going on, continuing, and you will keep track of the adjacent nodes. So until the queue is empty, you will have to repeat the process. For example, this is the graph, and this is the adjacency matrix representation of the graph. Now let us consider A to be the source vertex. That A is marked as visitor. Using this adjacency matrix, when we are finding the adjacent nodes to A, we find B and C are the adjacent nodes of A. So these B and C are enqueued like this. We are putting it in a queue. Now, B is dequeued, it's removed, and you are finding the adjacent vertices of this B. Using the adjacency matrix, you can find these are all the 3 nodes. As A is already visited, leave that. The remaining nodes C and D. C is already in the queue. So vertex D alone is enqueued here. Now, D is enqueued. From the queue, C is dequeued now, and we find the adjacent vertices A, B, and D, out of which this A, B are already visited, and vertex D is also in the queue. No enqueue operation takes place here. Now C is dequeued. Next, the last node, vertex D is dequeued. The process is terminating as we are visiting all the vertices, and the queue is also empty. This is the breadth first spanning tree. The application of BFS is we can check whether the graph is connected or not. The next method is depth first search. This depth first works by selecting one vertex as a start vertex, and you mark it as visited. Each unvisited vertex adjacent to this B, you are searching it in turn using DFS. So you are continuing the process till a dead end, which means there is a vertex with no adjacent unvisited vertices are found. You will have to repeat it. These are the steps to implement DFS. You choose any node in the graph, you mark it as search node, mark it as visited. Using the adjacency matrix, find a node which is adjacent to the search node that is not visited yet. Now designate that as the new search node and mark it as visited. Repeat this step 2 using the new search node. If there are no nodes which are satisfying this step is found, you return to the previous node and you have to continue from there. So whenever a turn to the previous node is not possible, then we can understand that the search from the originally chosen search node is complete. Suppose if the graph is containing unvisited nodes, choose any node that has not been visited and repeat these steps again. Now this is the graph. The corresponding adjacency matrix is this. Now let us see how DFS is performed. We start with A. Now from A, we are finding the immediate adjacent node to A is B. So from A, we move to B. Now considering B, find the next adjacent node to B. The next adjacent node is going to be D. Now consider D, find the unvisited node. The next adjacent node is C. So how it is implemented? We started with A and marked it as visited. The immediate adjacent unvisited node of A is going to be B. So now mark B as visited. Now from B, the next adjacent vertex is D, mark it as visited. Now from D, the next unvisited vertex is going to be C, mark it as visited. This is how the implementation is done. The resultant depth for spanning tree is this, A, B, D, C. The main applications of DFS are to check whether the undirected graph is connected or not. And moreover, we can check the acyclicity of the directed graph. Thank you.